So let's talk about Fourier transform of a function f in L1. Okay, and dimension. So we will define it the following way: the integral fx is 2 pi I and now psi will be in Rn. So we are going to change the notation because now we are talking about f in L1 and we are not getting Fourier coefficients for the Fourier series. Now we are having a transform that with a function, we insert a function of L1 and we will see what we'll obtain. Here x multiplied by psi, let's say x1 psi 1 plus xn psi n. Okay, so we will forget about the 2 pi that usually appeared in this side of the integral, and now the integral will be in Rn. So this is a different consideration for the Fourier transform. Now I'm not talking about Fourier series. Okay, so let's consider some properties of the Fourier transform that we just defined. First of all, the Fourier transform that one can express that takes a function in L1. It's a linear transformation that goes from L1 to L infinity, always we're talking in Rn. And the norm of the transform infinity is less or equal than the norm of f1. Okay. Another consideration, transform f is continuous. The transform of f goes to 0 as the absolute value of psi goes to infinity. This is Riemann-Lebesgue theory. Okay. So, okay, another property, if we call tau h of fx as the translation, then we will have the following property. If we transform t tau of h transform, it will be equal to e minus 2 pi I h psi multiplied by the transform of e psi. Okay. In the same way, if we call delta a of f of x as f of ax, we denotes a dilation by a greater than 0, then delta A f psi, the transform of this will be A minus n f transform A minus 1 psi. Okay. Then G is in L1 and recall the f g, this is the convolution of f and g. Then the convolution of f and g transform will be the multiplication of each of the functions transform. We are already seen this. Okay, and another property, G and L1, then the integral Rn of f y gy ey will be equal to the integral Rn fy gy. Okay, so now we establish some important properties of the Fourier transform in L1. Okay, so another property, suppose xk denotes the kth coordinate of x. Then suppose that xk multiplied by f is in L1 of Rn. Then f is differentiable with respect to ck, and partial derivative f transform ck minus 2 pi a xk fx psi. So the Fourier transform of the product xkf is equal to a multiple of the partial derivative of f psi or c. I've been calling psi or c the actual pronunciation in Greek language. I think it is c. Okay, so these are all important properties of Fourier transform that we didn't mention them, but we were only talking about Fourier coefficients for Fourier series. Now we're talking about Fourier transform as a linear operator that goes from L1 to L infinity of Rn.